everybody. I actually have to correct the web address that I gave you on Monday for the Azure plane group page. They changed the address. It used to be marie.epfl.ch/Azure. It is actually now azure.epfl.ch/Azure. So if you ever want to get some practice on plane groups, on finding symmetry elements, that is a good web page to go to, because you can create any kind of drawing. You can pull off drawings that somebody else already created, and you can practice on those. There's also your choice on that one, whether or not you draw the unit cell on whatever you give. Okay, so you could save a version with the unit cell, and you could give your friend one without the unit cell. So you can get to practice to find the unit cell, and you can double check yourself in the end. As far as the homework is concerned, several people were confused. How do I know whether this is a 2D or a 3D problem? There are plane groups and there are space groups. Plane groups are two-dimensional, space groups are three-dimensional. So the moment one of those expressions shows up in the header of the problem, you know whether you're working in 2 or 3 dimensions. Okay? Another thing, if I tell you there are symmetry elements missing and you need to find them, you need to find them. If I don't tell you that there are symmetry elements missing, work with what is on the paper. Don't add additional stuff, okay? If there was something missing, I would let you know. Don't change my drawings. It's the same as changing my axis system. I don't like that. You may end up with something that doesn't work, like a left-handed axis system, or some kind of space group that doesn't exist, right? So just work with what is given to you. Alright, so we did start on Monday a little bit with diffraction. And today we'll really start to get into the deep stuff of crystallography, reciprocal space. If you are a crystallographer, or if you want to be one day, you need to understand reciprocal space. Without it, you will not be able to properly handle your diffraction data. In a routine case where the computer does the solution for you, sure, you'll be fine. But if there's anything that actually involves interaction between you and the data, you need to understand reciprocal space. So, this is something that should be kind of becoming familiar and also partially annoying, right? Always we start with some kind of nice simple concept, and all of a sudden everything gets a little more complex and a little more complex and a little more complex. Has the advantage we can kind of start to understand things in little steps. So once again, here's a concepts versus reality. We talked about Bragg's law on Monday, right? And that was a fairly simple drawing, a fairly simple concept, fairly easy way of figuring out how you get diffraction. Now, reflection from lattice planes is not really something that happens in real life. The crystal is not going to make planes from which the X-rays reflect, okay? This is a concept that we constructed because it makes it easy for us to understand things. It makes it easy for us to derive something like Bragg's law, maybe even with high school kids, okay? What happens in reality is X-rays are scattered by electrons. And of course, atoms contain electrons, which means they are scattered by the electron cloud around the atoms. The reason for that is X-rays have a wavelength that is pretty similar to the size of the atoms, right? Angstroms. That matches. Interatomic distances are in the angstrom range. We might give them in a few hundred picometers, but that's the same as a couple of angstroms. Now the other thing is, if you have a periodic crystal, and this goes back to our whole unit cell concept, then we also have a periodic array of electron density, right? Because each unit cell has the same contents. And that means that we scatter our X-rays off a periodic array of electron density. One of those little facts that happens in crystallography is whenever you scatter an X-ray, there's a phase change of 180 degrees. Given that this is the case for every scattering event, it really doesn't make a difference at this point in time whether it is 180 or 0 or anything else, as long as all of these changes are the same. Now, first little look ahead, you can't only do diffraction with X-rays, there's also neutron diffraction. Neutrons, in contrast to the X-rays, are scattered by the nuclei of the atoms, which once again means if you have a periodic crystal, you have a periodic array of nuclei. So once again you can get diffraction. The nuclei are of course smaller than the neutron wavelength, and we will see once we get more into the details of X-ray and neutron diffraction that that can make a big difference. Another thing is the neutrons don't only interact with the nuclei but also with magnetic moments, so with unpaired electron spins. This just shows you what is meant by a phase change on scattering. So here's an atom, there's an X-ray coming in, and when it gets scattered by the electrons, there's a phase change by 180 degrees. So basically you have a discontinuity of your sine or cosine function. That is what that means. Now, good question is, we can come up with all these great concepts, right? Things get scattered or reflected or diffracted or whatever we want to call it. But what do we actually do in our experiment? What kind of data do we get? What do we measure? Well, what we really measure is the intensity distribution of the scattered radiation, and we do so as a function of the scattering angle behind our sample. That's what a diffraction experiment is. Okay? If we have a single crystal, we can do so in 3 dimensions. And just for simplicity, we don't just move the detector, we also usually move the crystal, because that way we don't have to move anything as far. For a powder experiment, usually you get your information in 1 dimension. Okay? Most X-ray powder instruments have a detector that moves on 1 arm, so you get 1-dimensional data. Now, what is important is that the electron density distribution inside the crystal directly, well actually not directly, does affect or determine the intensity distribution of your scattered radiation. It's not a linear relation, that's why I hesitated when I said direct. So it's not a simple relationship, but the two of them are intimately related. And of course that means that if we can go back from this intensity distribution to figuring out what that electron density distribution in the crystal is, and we know it's a periodic array, we can figure out what the unit cell looks like. And that is what we are really after when we do our diffraction experiments. Now, we can't measure this electron density directly. That would be nice. That would be great. If we had a microscope where we could see the atoms, shoot, none of you would be in this class. Okay? Because we would simply go there, we would throw our material on the microscope, we would see where all the atoms are, we would take a note of it, and we would know our structure of our material. Life isn't that easy. Okay? Even the best electron microscopes, you can get close to atomic resolution, but it's not a simple picture. Okay? You can't just slice through your material and simply figure out where those atoms are. So, a good way to get the structure of a material is still diffraction, and we do not measure the electron density directly. What we measure is the intensity distribution of the X-rays that are scattered by the material. Now, as a matter of fact, these two are related by what is called a Fourier transform. And the moment you see that word, you can also imagine that crystallographers really like computers. Okay? In the old days, people had to do things manually. Nobody in their right mind would attempt to solve a crystal structure without using a computer these days. Maybe they'll do it for a simple system just to demonstrate to people how it works, but not on a real life problem. Okay? It's not going to happen. And what we call this often is direct space, which is the electron density in the crystal, and reciprocal space, which is where our diffraction data is collected. Given that you as a crystallographer need to interact with your diffraction data, you now know why I claim that you need to understand reciprocal space if you want to get anywhere with your diffraction data. Your data is collected in reciprocal space. So, we sample reciprocal space, and that also means that we usually don't directly observe what we have so nicely talked about so far, which would be the crystal lattice, right? The unit cell. Because the unit cell would directly be that electron density distribution. Yes? Direct space is actually the crystal with its periodic array of electron density. Okay? So your sample is basically direct space. But because your data is related to what your sample looks like by a Fourier transform, your data is collected in reciprocal space.
It's like mold, forming a mold around the sample data.
Forming a what? A mold?
Yeah, so I'm envisioning.
It's not really a mold. It's basically a mathematical transformation. Okay? It's kind of like you image something through a lens. The image is related to what you imaged, right? But, for example, if you have one simple pinhole lens, everything will be upside down, right? That would be an example of some kind of a relationship that changes the object, but that has a close relationship to the object. This one is a bit more complicated. You don't just mirror everything for one point, okay? But that is kind of what you do. You take that crystal system, you put it through that Fourier transform. We'll be talking about those a lot more. Actually, there's a handout in the future that is called Fourier transforms, okay? And then you get your diffraction data. It's not a simple linear relationship, but there is a relationship. Now, given that we work in reciprocal space with our data collection, we can actually define something that we can call a reciprocal lattice, which is related to the crystal lattice. And you may remember from the last class that we talked about gratings and how things that were spaced far apart in the grating gave a diffraction pattern that was closely spaced, or how something closely spaced gave a far apart diffraction pattern. This is the kind of thing that we are talking about here. The crystal corresponds to that grating. Our diffraction data corresponds to the diffraction data from the laser that we saw. Okay? So, that one was periodic, right? Looked pretty nice and regular. The same way you'll get a very nice and regular looking pattern in reciprocal space. And we can define a reciprocal lattice. And that is from which we work most of the time. Here are these relationships between real and reciprocal space. Okay. Crystal or real space has a crystal lattice and of course unit cell contents. That's all you need to describe your crystal, right? Describe the contents of one unit cell and describe how that unit cell repeats in 3 dimensions. That is what we call a crystal. Then we have a Fourier transform that relates it to a diffraction pattern. And that diffraction pattern once again has 2 parts. One part that corresponds to a crystal lattice, and that's the reciprocal lattice. This is what we will be talking about in this handout. And then there is a part that corresponds to the unit cell contents. We will not talk about that today or in the next lecture. We will talk about it in about a week, 2 weeks. And it's called structure factors. And all of these are related by Fourier transforms. So, this new beast, the reciprocal lattice, what is it like? Well, first of all, it has the same symmetry as the crystal lattice. Okay? So if you have a cubic crystal, your reciprocal lattice is going to look cubic. That's pretty useful, isn't it? Because that means we can pretty quickly get some idea of our unit cell shape if we look at the reciprocal lattice. One thing that you can do is you can actually take a crystal lattice and graphically derive your reciprocal lattice. And that of course means if you know enough, you can probably go the other way around, right? How do you do that? Well, you will draw lattice planes. We've talked about those, right? Miller indices. They were not just there to tease you, okay? There's a reason why we talked about them. They're actually important. So you draw these lattice planes corresponding to certain sets of Miller indices, You then choose an origin and you draw normals to the lattice planes. So those of you who have not yet invested in a goniometer, this is a good time to do so. You need something with which you can measure angles. There will be such problems on future homework sets. After you draw these normals, you mark points along these normals. Okay? And these points should be spaced equal spacings. And these spacings are called d star HKL. Now this is something that you'll find over and over again. When we talk about reciprocal space, we put a little star on lattice constants, on spacings, just to designate that this is reciprocal space. Okay? So in real space we have A, B, C as lattice constants. In reciprocal space we'll have A star, B star, C star as our reciprocal lattice constants. In real space we have crystal plane spacings D. In reciprocal space we have reciprocal lattice spacings D star. Okay, so the star always means you're in reciprocal space. How do you figure out how long D star is? Well, there's a very simple relationship between D star and D. D star is 1 over D. Note, these are not vectors, these are simple numbers. The magnitude of D star is equal to 1 over the magnitude of D. Okay? The direction is given by that normal. So, how do we figure out the reciprocal lattice constants? Well, that is when we actually use the 100, 010 and 001 families of planes. Okay? In the real lattice. We draw the normals to those and we mark points along them. 1 over D100 is going to be D star 100. And that is what we would call our A star. The same with B star and C star. Now, if you started with a crystal system where you had 90-degree angles, okay, A star has to be along the normal of the 100 family of planes. The 100 family of planes was perpendicular to the A-axis in real space, right? So your A star is pointing the same way as your A in that case. Its length will be different, but it's pointing in the same direction. If you do not start with 90-degree angles, your reciprocal lattice constants will not point in the same directions as your real space lattice constants. Okay? Because your normal will no longer coincide with the original lattice constants. You're moving your axis system around. And on homework 3 you'll see this because you will be asked to do something like this. Okay? Well, let's look at an example. Here's a reciprocal lattice that is graphically constructed. This is one of those drawings where on first glance you're like, oh my god, what are they doing? Right? A lot of points. So, what they give you here is actually the real lattice. Okay? These are those repeats. Here are the lattice points. Remember we talked about those with Bravais lattices. So each of these would be a unit cell. And as you can see, this is not a 90-degree axis system, right? There's some angle between these two that is not 90 degree. Now, just to make clear what they really did, let's make use of the fact that we have a whiteboard behind this one. So, here's our A, and here's our B axis, right? And this distance would be A, this distance would be B. Everybody agreed? So, Where's my 100 family of planes? It's these lines, right? They are parallel. Oh, actually it's not B, it's the C axis. They didn't draw the B axis, that one would be perpendicular to the board, okay? So, my 100 family of planes has to be parallel to the B axis and parallel to the C axis, right? Or it wouldn't have these zero indices. It cannot cut them. Here's my family of planes. It cuts at 1 unit cell, so it's the 100 family of planes. But it's not perpendicular to my A-axis, is it? Because there's no requirement for it to be that. There's just a requirement for it to be parallel to the other axes, to be the 100 family of planes. That means if I draw a normal along this one, it's not parallel to the A-axis, right? It's at an angle from it. And so that is this line that they drew here, okay? Now, of course, we would need some kind of length of the A and C axis to really draw anything, okay? But we pick our origin up here, and if this, for example, was 1, okay, very simple A-axis 1, then the distance we should mark on this one should also be 1, because 1 over 1 is 1, right? If this length was 2, what distance should we mark here? 1/2, right? So it doesn't really matter what that distance is. Let's say it is 1. Then we start marking things at about equal distances, okay? Of course I don't have a ruler with me, but it would look something like that. About the same distance as this one, okay? And you just repeat that. And you would call this distance between the origin and the first point you marked D star 100. Okay? That one was 10, you would mark at 1/10. Okay? You just plug in the numbers. Now the same way, on this drawing, we can find the 001 family of planes, right? Because this is the AC plane. Does anybody see the 001 family of planes? It's these, right? They are parallel to the A-axis, so you get that O. They are parallel to our B-axis, which we really don't see, and they intersect the C-axis at 1. So there's your 001 family of planes. What do we have to do? Well, according to the rules, we draw a normal to it, right? As I said, we need to be able to measure angles. Somebody drew that normal for us. Here it is. There's a little symbol that indicates it's the normal. This spacing seems to be a little bit bigger than that one, right? So given that we said the other one maybe it was 1, let's make it 1.5 or 3/2. What distance do I need to mark points now? 2/3. So it might be, you know, something like this. Everybody agreed? I would have to take a ruler to measure it exactly. But this is a distance that is shorter than that distance, 2/3 instead of 3/2, something like that. Now, this one is my D star 001, right? Now, if I take away the crystal lattice, then I could just draw a new lattice from what I have on the board, couldn't I? Because here's my unit cell, right? No. And I could just repeat it. Because I know that I must have a regular repeat pattern. And of course I would make these straight lines and equal spacings. And at each of these intersections I could draw one of those points. Each of these intersections is a place where you would see diffraction. Okay? So this would be that reciprocal lattice that we will collect with our diffraction data. Now, can I define any other D spacings in reciprocal space? Sure. First of all, crystallographers assign numbers to each of these points. Okay? And this is one where you can actually do simple counting. Isn't that nice? Who likes simple counting? Good. We call this point up here, that's our origin, okay? That one over there, we call 100. That one there, we call 200. This one, we call 300. Over here, we have 001, 002, 003, 004. Anybody want to guess what the numbers for that point are? 101. So you basically now have a grid that very much resembles what you learned a long time ago in school, where all you do is you mark equal distances and you count. Now, why is that? Because it's reciprocal, right? Our 200 family of planes in crystal space would cut at a half unit cell. Well, that means we all of a sudden double the distance, right? So our distance from the origin has to be twice as far for that one. So in reciprocal space, all of a sudden all of our counting works nicely again. So, that's what a reciprocal lattice looks like. Could I have figured out that 101 some other way? I sure could have, okay? I could have gone ahead and I could have drawn the 101 family of planes, right? We've learned how to do that. Cuts at 1, cuts at 1. We draw a line and we draw the parallel lines for all of the adjacent unit cells. Now, according to the rules of the reciprocal lattice, can I draw a normal to this family of planes? Sure. And if I know what my spacing between the 101 crystal planes is, I take 1 over that spacing, and that is the distance I have to go on this line to mark my D star 101. And what you will find is that that will correspond exactly to that point that we found without using that family of planes, if you do your drawing right, with the right measurements, okay? So, everything kind of does go back to where it started. And you will get this reciprocal lattice. You'll have an A star and a C star axis in it, okay? Yes?
how do you tell your normal? How do you compare the normal?
You use a goniometer, something that indicates 90 degrees, and you measure 90 degrees from your lattice plane. Okay? That's why you need something that allows you to measure angles. You can't just ballpark it. It's not going to work.
So the first normal is 90 degrees to the z-axis, going way down.
There is, this one is the one that is 90 degrees to the z-axis. Yes. And on a piece of paper with a little grid on it, you might be able to draw that one without measuring angles. Okay? For the other ones, I doubt that you'll always get 90 degrees. And no, 88 degrees is not 90 degrees. Okay? It's got to be 90 degrees. Otherwise, all of a sudden, these additional distances won't work anymore. So these measurements have to be done very precisely. So this is what you measure, and of course you can transform it back to that one. Luckily, in most cases, the computer does it for you. But that is what the relationship is. Okay? And that is why if crystallographers collect certain things, they may just look at a piece of data and already know something, where somebody with no knowledge is staying there thinking, what kind of magic is this? Okay? It's not magic. It's knowing reciprocal space. Well, can we deal with things differently too? How about those of us who don't like to draw things, who don't like to measure angles? Well, on homeworks or exams, when told to do so, you can't get around it. Okay? That's where the dictatorship still works. Other than that, sure, you can do math. Not a problem. Here's the mathematical definition of your reciprocal lattice constants. Notice, now they are vectors. On the previous slide, we got the direction by drawing these normals and going along the normals, okay? If we don't draw something, we need to give the direction, so we work with vectors. Your reciprocal lattice constants A star, you get by taking the cross product of the vectors B and C in real space and dividing by the unit cell volume. Now the unit cell volume you get by taking the cross product of two vectors and doing the dot product with the third vector. Now, see a couple of confused stares here. Who needs a little refresher on vector math? Few of us, right? That's alright, we usually do need that, because if we haven't dealt with vectors for a while, they seem pretty strange beasts. So, let's put a couple of equations down here. Whoa, did we once have a sponge?
That's right.
Basically, what you really need here are two vector roots, right? You need to be able to do a dot product and a cross product. That would be a cross product. First thing to consider is, what do we get out of a cross product? Do we get a scalar, a number, or a vector? Vector. Very good. There are several different ways of indicating that one. What this means is it is a unit vector, so that vector has a length of 1, and it is perpendicular to both A and B. Okay? You then multiply that vector by the length of the vector A, the length of the vector B, and the sine of the angle between them. And usually we call the angle between A and B gamma, right? So that's our cross product. That tells you that A star will be perpendicular to both B and C, right? B star is going to be perpendicular to C and A. C star is going to be perpendicular to A and B. Well, that goes back to what we just drew, right? Because we draw the normal to something that was parallel to 2. That means it's perpendicular to both of those. Right? Now, how do we do the dot product? First of all, what do we get out of it? A scalar or a vector? Scalar, right? It's a number. Well, that's a good thing because our unit cell volume, the last time I checked, wasn't a vector. It doesn't have a direction, it just has a size, right? So, how do we do a dot product? Well, again, we take the magnitude, which we indicate by these norm lines, and this time we use the cosine of the angle between them. Now, for this one down here, does it matter whether I write A times B or B times A? No, right? Because I multiply two numbers, who cares what order I do that? And the cosine is centrosymmetric, right? Doesn't matter whether I'm in the positive or in the negative, really. Does it matter here which direction? Absolutely. Because the sign basically starts at 0, okay? It's not symmetrical around 0. So it matters how I measure that angle, right? How do we measure angles? Dang, one of those things. Never thought you had to do them again, right? You measure angles between the tips of the vectors, okay? And, of course, you usually measure counterclockwise, right? So you could be using this angle if you multiply cross product, multiply that with that, or you could have to go a heck of a long way and get a different angle, which is of course the equivalent as using the negative angle. Okay, if you measure the wrong way around, it would be the equivalent as 360 minus that one. So on this one it matters in which direction, in which order you do the cross product. How do you remember them? Well, everybody here knows the alphabet, right? So you always keep going up in alphabet until you run out of lattice constants. That's how I remember it. A star, B, C. A, B, C. That makes sense. B star, going up in alphabet means I take C first. Well, I'm out of lattice constants, so I go back to the beginning. A. C star, A cross B. Okay? Just a little helper on how you can remember in which order you have to multiply these things. So, that is a mathematical description of your reciprocal lattice constants. Make sure you know those two vector rules that we just wrote down. You will need them in the future. Okay? Now, everything we've done so far has assumed we have that crystal, we have that periodic array, and then we did some graphical constructions, and all of that is kind of nice and good. But where does it really come from? Okay? Here's a little drawing. You can download that one in the handout, obviously. It's a blob of material. We make no assumptions about that blob of material at all, except that it contains some atoms. Oh, last time I checked, that's a pretty good assumption for most things. Right? And we'll be looking at two atoms, two arbitrary atoms somewhere in this material that are separated by a distance r. And this is actually a bold r, so this should be a vector r. Okay? There's a distance and a direction in which these atoms are separated. We'll have a look at what that does if we shoot X-rays at it. We'll go from the two atoms to a large number of atoms. We'll figure out how all of this reciprocal space stuff actually comes about. Now, I will be covering the projector thing, and we'll be doing some deriving on the board. This is going to be some much more complex math than a lot of the things that we do in this class. I will not ask you to ever reproduce that on an exam, okay? So, if you can follow all of it, it's not such a big deal. I do want to do it because the way some people introduce reciprocal space to you is they say, oh, draw these normals and do it, and there's your reciprocal lattice. It works, sure. But does that give you a reason why it should be that way? Who made up those rules? Where do they come from? Why does it work? Okay, this is the mathematical derivation of the scattering equation. This one will show you where these things come from. Once we are done with it, you can remember it, you can remember parts of it, or you can forget about it. Okay? Your choice. I will not ask you about that one on the exam. But it is useful for really understanding what reciprocal space is, where it comes from, and what its properties are. Okay? That's why we will do it. So, our blob of material. So I'll first cheat and make use of this one. So there's my blob of material. And I'll actually take two atoms that are a little bit further separated, okay, because that way it's easier to see. That's my distance r. And I have X-rays coming in here. And each of these X-rays is of course scattered. Right? That's what we said happens when X-rays hit atoms. So, there's our little drawing. This kind of reminds us a little bit of Bragg's law, right? Main difference is things aren't quite as regular here because we haven't been talking about parallel lattice planes. We are talking about two arbitrary atoms, right? And of course I should move this one a little bit further to make sure this drawing actually works. Here's some incoming X-rays. We can describe them by a vector. There are some scattered X-rays. We need a different vector for those because they are scattered in a different direction, right? But as they are parallel, and assuming that they get scattered in the same way by the two atoms, we can assign the same vector to both incoming and both outgoing rays. Now, what according to Bragg's law do we have to watch out for if we want to know whether we get constructive or destructive interference? Phase change, which is related to a path difference, right? So what we need to figure out is how much does each of these X-rays travel? And we do that by what? by drawing normals, right? So we'll draw some normals. And I chose to draw them so that we actually kind of split the path difference. One of the rays travels more before hitting the atom, the other one travels more afterwards. It would work either way, okay? You could have both of those path differences at the bottom. Doesn't matter. It'll come out to the same. Now, got a drawing, got some path differences. So what we need is to figure out these two, right? Because those are the two path differences between our rays. And let's call them delta L1, delta L2. That's what we are after. Now we need to figure out what they are. Looks like some ugly stuff, doesn't it? Well, let's write down a couple of rules that will be useful. Okay? One of them we already had up. The dot product between two vectors. Given that we haven't really assigned any angle names here, I'll just say the cosine of the angle between A and B. Okay? So that's one of our rules. Second rule that would be useful, according to what we have over there. So of course, looks like we have some triangles with 90-degree angles, right? And we did come up with those sine and cosine relationships. The sine alpha is equal to A over C. The cosine of alpha is equal to B over C. Another one of those rules that is useful to remember. Third thing that is very useful is to figure out how sine and cosine are related, because we'll be converting them. You don't know that yet, but I may as well put down the rules, right? If I draw a cosine, where do I start? Plus 1. Where does it go to 0? 90 degree, right? What does it do after that? Goes to minus 1, right? Goes back to 0. Goes back to plus 1. So our cosine looks something like that. What does our sine look like? Starts from 0, but otherwise pretty much the same, right? So, how are sine and cosine related? A 90-degree difference, right? So we can write that the sine of an angle minus 90 degree is equal to the cosine of that very same angle. Okay? That's the relation between those two. Now we do have to make a couple of assumptions. We have two atoms separated by a vector r, right? We already said that. We have incoming radiation, right? So we have parallel X-rays which are in phase, because otherwise we have an unknown phase difference to start with. And then we may as well not even start with our math, right? And we've chosen to describe them by a vector, right? And given that all I really care about is the direction of the X-rays, right? I mean, I'll know a wavelength of them, but overall I mainly care about the direction of the X-rays. We'll just choose the vector that we use to describe it as a unit vector. It's just more convenient, okay? So the length of the vector with which we describe the X-rays is going to be 1. Then we have the scattered X-rays. What shall we assume about those? They are also parallel, right? So we can describe them by one vector, which we chose to call S. And what should we assume about the length of that vector? Once again, it will be convenient to use a unit vector, right? So the length of S will also be 1. The last assumption we need to make is that all scattering events will give the same phase change. Okay? That one happens to be 180 for X-rays. As long as it is the same, I really don't care what it is, but it has to be the same. Because otherwise, once again, we introduce a path difference and we don't know what it is, right? So, and we'll call these here rule 4. And to have all the rules together, I'll put it down here. Now I'll let you folks copy that one. We'll leave the rules up. We'll need the board space over there. Alright, so now let's try to figure out what those path differences actually are. So let's name some angles, right? What did we do for Bragg's law? We worked with the angle across from the path difference. Let's call that one beta. What can you tell me about that triangle? First of all, which rule should we use? 1, 2, 3, 4. Number 2. So according to number 2, the sign of beta is what? Delta L1 divided by the length of that vector that describes the distance, right? Because this is a 90-degree angle, so it's the side across divided by the hypotenuse. So sine beta is equal to delta L1 divided by r. Alright, that's not too tough. But is that really useful? Well, first of all, of course, we can rearrange that, right? Because what we really want is delta L1 so you can write delta L1 is equal to r times sine beta. Does not look very useful to me in the current shape. I don't know about you, but there's a length of a vector that I really don't know. There's an angle that I certainly don't know. So let's do a little bit of magic with it. One of the things we can do is we can actually look at the vector between, at the angle between two vectors, right? Now remember, you measure the angle between the tips of the vectors, right? But that means that this one is the very same angle, right? Pretty obviously. Now, here we have S0 pointing that way and R pointing that way. So I hope that all of you will agree that this would be the angle between the two vectors. I'm just using the two tails instead of the two tips. And let's call that one alpha. Can anybody tell me how alpha and beta are related? Difference of 90 degrees, right? So, if I would like to, I could write that my delta L1 is equal to R times the sine of alpha minus 90 degrees. Because alpha minus 90 is equal to beta. And those who pay careful attention probably have some idea where I'm going with this. Which rule should we use? Rule number 3? Sounds like a plan? So it's R times the cosine of alpha. Alright. Still doesn't really look a lot better, right? Unless you know where you're going. Now, can we multiply any expression by 1? Is that a legitimate mathematical operation? Yeah, right? It really doesn't matter. So, let's see. That means that I can say that delta L1 is really exactly the same as R times 1, because the magnitude of S0 is 1, times the cosine of alpha. Right? Mathematically, all of this is perfectly good. Does that expression somehow look familiar? It's rule 1, isn't it? So delta L1 is equal to R times S0. So now we only have two things in there, okay? And one of them gives us directly the relationship between the two atoms. And while we may not know that one because we haven't made any assumptions, if we talk about a real-life material, we should know that one, right? And the other one simply gives us how we are shooting X-rays at it. So that's not a bad expression to use. Now, see whether we can do the same thing in the other one. Okay? So use the angle across from delta L2. And let's call it beta prime because we already used beta, we can't reuse it, right? So, what do we get for that one? The sign of beta prime is what? Delta L2, right? Divided by R. Sine of this angle is equal to the side across from it divided by the length of the hypotenuse. And once again, can we define a different angle? Well, here's the angle between R and S, right? Let's call it alpha prime because we called the last one alpha. And so if we move it around, so we would have delta L2 is equal to R times sine beta prime. And we get delta L2 is equal to R times the sine of alpha prime minus 90 degrees, right? Because once again, these two angles are related by that. And as we previously figured out, that means I can write the cosine. Again, similar to the last case, we can multiply by 1. This time we'll take a different one, right? Because we want to work with something where an angle over here is involved. It's of course a prime. Then you should probably use S, but the length of S is also 1. So we came up with some very simple expressions here. That looks a lot better than all of that stuff we had on the board, doesn't it? Got our delta L1, got our delta L2. If you look at that drawing, what would be the total path difference? Delta L2 minus delta L1, right? So that would be r times s minus r times s0, right? So here's your path difference, r times s minus s0. Did you ever imagine that an arbitrary location of atoms would give you such a simple path difference? Doesn't look too bad, does it? Of course, we still need to do something else because this really doesn't tell us anything about interference yet, right? But that is the path difference between the scattered X-rays of two arbitrary atoms in arbitrary locations that are related by that vector r. Okay? So, that is how those equations on your handout come about. Okay? Because this path difference is given at the bottom of that handout. Seems like magic unless somebody actually shows you how you get there. Now, with the knowledge that whoever put down that path difference indeed knew what they were doing, let's continue. Here's our path difference. What do we do with it? Well, first of all, often what you will find in crystallographic texts is a so-called scattering vector, capital S. Okay? And that one is simply S minus S0, our scattered vector minus our incoming scattered X-ray vector. So it's basically a change in scattering if you think about it. Okay? Now, the path difference is related to a phase difference, right? And what we know about that is that it matters how much of a whole wavelength we travel, right? And so we know that the periodicity would be 2 pi or lambda. And so you have this factor of 2 pi over lambda that translates a path difference into a phase difference, because those are the units for our phases. So your phase difference is simply 2 pi over lambda times your path difference. And of course you can plug in these vectors. Once again, this one is given because a lot of crystallographic textbooks may use this k. So they'll give you a phase difference that is k times r. And if you just happen to open that book on that page and never saw any of this, you'll be like, what the heck is this? Okay? This is where it comes from. Now, that is our phase difference. We yet have to take another step, and that is what we are really interested in, is how does our scattering amplitude change, right? And all those phase differences and stuff, that's just a way to get to where we want to be. Now, our scattering amplitude we can describe as A of S, right? The amplitude as a function of the scattered vector. And the change in it, we would just say, is D, right? So the change in scattering amplitude will be related by a Fourier transform to this phase difference. Will also be related to the electron density, right? Where are our atoms? What are the separations between them? And we need to look at a volume element over which we want to see the scattering change. And of course this D means if we want to get to the scattering amplitude itself, we need to integrate. And this is the prime signature of what we call a Fourier transform. Okay? You have an e to the I something, where there's a variable in there, a function of the very same variable, and integrated over space in this case. This is a Fourier transform. Not nice to solve by hand. The computer does it for you. So, this is what comes from all this derivation that we did. Okay? This is what we are really after. Now, so happens that the scattering amplitude and the electron density are always correlated by a Fourier transform. You can go both ways, okay? So you can calculate the amplitude from your density in the unit cell, or you can calculate your density from the scattering amplitude. Guess what we usually do? Most of the time we measure this, right, which means we calculate that. But if somebody gives you a crystal structure, you could actually calculate what that amplitude should look like. Now there's only one problem. Life would be beautiful if we really measured that. Who has ever managed to measure an amplitude of a wave? Sounds a bit tricky, right? Because that wave doesn't stand still. So what we usually measure is what? Intensities, right? And in many cases we really don't pay that much attention to the fact that an intensity is not equal to the amplitude. However, it's not. Okay? Intensity is actually the amplitude multiplied by its complex conjugate. And intensity is not a complex number, is it? It's a real number. If we multiply by the complex conjugate, for those of you who haven't dealt with complex numbers for a while, what we do is we change the sign in front of the I. Okay? If you think about it, e to the ikr, or e to the minus ikr in this case, is cosine of kr minus I sine of kr, right? That's the definition of that complex e function. If we take the complex conjugate, the minus becomes a plus, so we have the cosine of kr plus I times the sine kr, right? What will happen is that any of the terms that would still have an I end up cancelling, because you have half of them with a plus, half of them with a minus. The sum is 0. You also have a minus I squared. Well, minus I squared is minus 1, right? So what you end up with is an intensity that is equal to cosine squared plus sine squared. Okay? So, a lot of this stuff drops out. Now, we will be getting back to this quite a bit, because this is often called the problem of crystallography. Okay? We would love to be able to measure that directly and not lose the phase. Now, the important thing to keep in mind today though is, have you made any assumptions about our material so far? No. Did we make any assumptions about the fact that it's periodic? No, right? So this is valid for any blob of material that contains atoms. Really doesn't matter. Of course, we wouldn't do it with 2 atoms. We would do the summation over all of the atoms, all of these interatomic distances, right? But we haven't made any assumptions about periodicity. That is why we haven't ended up yet with a very simple equation. So, what happens if we implement periodicity now? Well, let's look at it. Let's make use of what we learned about crystals and periodicity. What we know is, if we want to describe an entire crystal, how much of it do we need to describe? 1 unit cell. If we can describe that 1 unit cell, all we need is the translation, right? So our rho of R can really be described much more simply as a rho of R0, where all of these are within 1 unit cell, okay, plus some kind of translation. And we know what these translations have to look like, right? They have to be integers times the lattice constants. Right? You reproduce this electron density as you go along the lattice constants. Now that makes life a lot easier. Okay? Because instead of having all these vectors from one atom to everything else in the crystal, we only need them in one unit cell, and then we use the unit cell translations. And we can plug that one into this integral. Okay? Once again, no magic done so far. It's the same equation from the last page. All we did was we replaced rho of r by these expressions, and of course we replaced the r here with the r0 plus tau 1. The real trick comes when we realize that this is a sum. It's only defined when m1, m2, m3 are integers, right? So we really don't need to leave it in the integral, do we? We can write that one as a sum. So it's the sum over all m1, where m1 is any integer, of this part of the expression. And what we made use of here is another very good math rule to remember, okay? E to the a plus b is equal to e to the power of a times e to the power of b. So if we have an e function with a sum, we can pull it apart and multiply individual e functions. That is what was done here, okay? We pulled that tau out. We said this is e to the minus ik r0 times e to the minus ik tau 1. And then we said, well, tau 1 itself is a sum, so once again we can multiply these. And that is how you can get to the point where you can draw these out of the integral and replace them by a summation sign. Kind of looks like, if anything, life is getting worse, right? The expression becomes longer and longer and longer. But bear with me another slide or two and you'll know why. Let's look at that sum only. Let's ignore the rest of it. Okay? Now we make use of that fact that a complex e function can be expressed as a cosine and a sine. And all we do is we plug back in what these are. So that k we know is 2 pi over lambda times s. Right? And so we plug these in. And then we can write one of these e functions as the cosine of this expression minus I times the sine of this expression. And we have to sum over all integers m1. Okay? You can't just leave some of them out. This is not a pick and choose exercise. This is a sum over all integers. That means that that sine argument will in the end actually always drop out. Okay? But the cosine can lead to a sum that is not equal 0. When does it do that? Well, it will do so whenever our argument here happens to be an integer times lambda. Okay? Because if this is an integer times lambda, then we have 2 pi times an integer times lambda divided by lambda. So that's 2 pi times an integer, last time I checked. Cosine of 2 pi times an integer is one, right? Cosine is a 2 pi periodicity. It's 1 at 0, at 2 pi, at 4 pi, at 6 pi, at you name it pi. So, whenever this a times s happens to be an integer times lambda, this one will give a sum that is not 0. Okay? Same holds true for the sum over here. If this b times s happens to be an integer times lambda, you will get a sum that is not 0. And the same holds true for the third one. Okay? Now, why is that important? Well, if you look at this, you multiply by these three sums. If one of them is 0, what does the entire expression become? 0. Okay? So, the only time that this sum will not be 0 is when this is fulfilled. Because then all the cosine expressions will be 1. None of them will be negative, and so on. If you use, for example, a half here, you would very quickly extinguish all of them. If you use some number in between, you would have to sum over a slightly longer interval of m's, okay? But in the end, you will once again end up with something where the whole sum becomes 0. And you're welcome to try that out, okay? I actually once did, because I had to convince myself of that. It's like, really? Really happens. So, if we look back at these, this is actually our good old Lowry conditions back that we talked about in the last lecture, okay? Path differences in 3 directions have to be an integer times lambda. Remember that one? Now, this time we wrote it as vectors still, right? So, this is where things allow us to actually gain some knowledge about reciprocal space. If you write things like this, what you're really writing is a series of planes, okay? Spaced at a distance 1 over a. And this drawing shows you that one. Here's your scattering vector. Here's your vector related to your a. Basically, when you multiply these two vectors, any point that happens to fulfill this, which means any direction of this vector, will be a solution. And that gives you a plane, right? You can move things around here. Because what this is the projection of one vector onto the other, the way it is written. So you get this series of planes spaced 1 over a apart. Each of these planes is a solution for this very first condition, okay? n1 over a. This is a unit vector in the direction of a, and you take the projection of the vector s over lambda onto it. You get this series of planes. So that first equation, the solution of that first equation is a series of planes. If you had a one-dimensional crystal, this is where you would see intensities. Okay? And that is the one thing that you never get from the graphical derivation of a reciprocal lattice. If you had a true one-dimensional crystal, you would not get spots in reciprocal space. You would get planes of intensity. And that's kind of a mind-boggling concept. But that is what comes from that general scattering equation. Now, guess what holds true for the second direction? What's going to be the solution of that one? Could it be a series of planes in the b direction, spaced 1 over b apart? Should be, right? Because this is once again a unit vector. You can take the projection of this vector onto it. And that means any point in a plane that is perpendicular to this unit vector will fulfill it. And you have these planes spaced 1 over b apart because n can change its number. How about the third direction? Should also give us a series of planes, right? So, one dimension is here. What happens if you form intersections between two series of planes that are not parallel to each other? What is the intersection? What does it look like? a line, right? Take one plane, you take another plane, they intersect in a line. Does everybody see that? Got an intersection that is a line. So what would you get from a two-dimensional crystal? You would get lines, right? Now, let's add a third dimension of planes. If we have to fulfill all three conditions simultaneously because we multiply, right? What is the intersection between three series of planes? The point. The reciprocal lattice point, which is what we usually measure in a diffraction experiment, the spot, right? That's where your spots come from. It's not because somebody came up with a clever way of drawing something and then we somehow get the instrument to reproduce what we can draw, okay? It's because of this. Because of the scattering equation, because of the solutions to the scattering equation, because of the fact that three intersecting series of planes that are not parallel to each other will result in spots. Now, your chances of seeing this in reciprocal space, very, very slim. Making a true one-dimensional crystal, if it is possible, it's certainly tough, okay? Seeing infinite lines, not likely. But what you may end up with, in some cases, okay, is some kind of feature in your diffraction pattern so what you want to see is this, right? Nice spots. What you may sometimes see, something that looks more like that, okay? Varying lengths. Usually when something like that shows up, the crystallographer you might be working with will say, I don't like this crystal. Or they may tell you something like, your platelets are too thin. Okay? And I've seen data like that. Okay, so this happens. You won't get the infinite lines, but you might get something like that. The reason why the crystallographer can say this is because they understand reciprocal space. They know if this was a true big crystal, infinite repeat in 3 dimensions, you'll get spots. You don't get spots, something is wrong with your crystal. Now, if you are lacking a good bit of the periodicity in 1 dimension, like you have a very thin platelet, right? So you have very few repeat units in one direction, you don't get a true family of planes for diffraction. So your features kind of start to extend in that direction. So if you have plate-like crystals and you see spots like that, you got a problem. You don't really have a long enough repeat pattern in one direction. That's why the crystallographer can tell you something like that. In a powder pattern, all you would get would be tails to your one-dimensional data, okay? But these things can actually show up in real life. If you have nice crystals, chances are they won't. But if you have a crystal that is very limited in 1 dimension, then they might. And the only way to make sense of that, okay, is by understanding how these things look in reciprocal space. You cannot figure out what this means from any kind of drawing of a reciprocal lattice, because that makes no sense, right? This comes from the scattering equation. And that is why I did want you to see the derivation of that. Yes, it was ugly math. No, I'm not going to hold you accountable for deriving that on an exam or homework or anything else. But the outcome of it, this slide, the solutions in reciprocal space, that's important. I will hold you accountable for understanding this one. Okay? So make sure that you get familiar with this, that you remember that the solution in each direction can be described by vectors. You get a series of parallel planes as solutions. Okay? Now we do have a few minutes left. However, this is some pretty heavy material. This will take a while to digest, okay? If you do not understand everything perfectly right now, that's absolutely normal. So, I suggest that we actually stop right here. Take some time, look back at this, make sure that you do understand the outcome of it, okay? Any questions at this point in time? And if they come later, do feel free to come and see me. And as I said, if you want to skip a few of the details of this, that's okay too, as long as you get the gist of it and what comes out of it. Alright? Homework is due on Monday. Make sure you have it ready by then.